So we got an object right here. Let's call it the Earth. We have an object orbiting around the Earth. Maybe it's the International Space Station. We call the International Space Station a satellite because it's orbiting around something else. Anything that orbits around something else is a satellite. Now, normally, when we talk about a satellite, we're talking about something that orbits around something else in space due to gravity. Okay, if that's the case, whether it's the International Space Station orbiting around the Earth or whether it's the moon out here orbiting around the Earth, in any case, we can analyze it in the same way. The International Space Station, the moon, whatever it is that's orbiting around the Earth, is held in place by a centripetal force. Every object that's moving in a circle experiences a centripetal force, whether we're talking about a car going around a turn, or a roller coaster going around a loop, or whether we're talking about the Earth going around the sun or the moon going around the Earth. There's a centripetal force. But there's always got to be something that causes that centripetal force. And when we're talking about satellites in space, it's always going to be the force of gravity that causes it. So we're going to set Fc equal to Fg. The centripetal force that acts toward the center of the circle is equal to the force that causes it, which is that force of gravity. The centripetal force is mv squared over r, and the gravitational force could be m times g. It could be technically m times g. The only problem is that we don't know what g is, what little g is, for most places, only if it's actually on the surface of the Earth. So we're going to change that equation. Instead of saying m times g, we're going to call it gm1 m2 over r squared. Now we're going to cancel out one of the r's, and we're also going to cancel out one of the m's. The mass that we canceled out was the mass of the satellite, the mass of the experiencer as it orbits around. That leaves us with m2, or we'll call it the mass of the producer. If the Earth is orbiting around the sun, we'd want the mass of the sun. If the space station is orbiting around the Earth, we'd want to use the mass of the Earth there. So we're left with an equation that looks like this. V squared is equal to g times the mass of the producer over r squared. You're going to rearrange this to solve for whatever you're looking for. Now, I'll get your question in 1 second there, Lewis. There is one more thing that we sometimes have to do in conjunction with this. We know that v squared is equal to g times the mass of the producer over r, not r squared. Lewis, that's what you're going to say, wasn't it? Thank you. Over r, because we canceled out one of those r's, right? Gm over r. But we also know that v, anytime we're talking about an object going around a circle, whether it's a satellite or a roller coaster or a car going around a turn on the highway, it doesn't matter. Anytime an object is going in a circle, v is equal to 2 pi r over t. So sometimes what you're going to have to do is solve for v this way and then plug it into there. Or sometimes you're going to solve for v this way and then plug it into there to solve for period, the time that it takes to go around once. Okay? I would say 65% of the time, you're going to use this equation on its own. Okay? The other 35% of the time, you're going to use this equation in conjunction with this equation, whether you're using that one first or second. It depends on the question. But probably about a third of the time, you're going to end up using those two equations in conjunction with each other. Now, yesterday for homework, we had two questions, page 279. Okay, I want to take a look at either one or both of these questions. Okay, if you guys don't ask me to go over any of them, then I'll pick one. If you do ask me to go over one or both, then we'll go over whichever ones you want. Okay, any issues with either of these two questions? One or two? Number two? How's number one, guys? Are we okay with number one, or should we go over that one as well? Good with it? All right. So let's take a look at number two then. It says the Chandra X-ray satellite takes X-ray pictures of high-energy objects in the universe. It's orbiting at an altitude of 114,000 kilometers. That's high up. Okay, think about that. The space station is just under 400 kilometers up. This satellite is 114,000 kilometers up. It's a long way up. Why is it so far up? Why do we not just put it basically on the space station? Like, let's throw it on the back. Let's make the space station tow it behind it. Yeah, that would be cheaper, right? Why would we put it 114,000 kilometers up? Any ideas? Yep. Yeah, yeah. Look, the space station is in space, right? But it's kind of the edge of space. There's still things, there's still gases up there from the Earth's atmosphere to obscure um, telescope images. So what we want to do there is get above all that. Let's get away from all the light from the Earth. Let's get away from any kind of gases, atmospheric gases that might obscure or refract light. Okay, let's get away from all the outside influences. Let's get as far up as we can get. 114,000 kilometers. We're going to get better images now of what we're trying to take pictures of. All right, so that's where it is. We want to find the orbital period. Okay, let's write down what we got here. Looks like we just have one number, actually. What is that? What is it that we have there? Part of the radius? What do you mean by that? Oh, okay. So let's draw a picture here. Here's the Earth. Okay, here's the radius of the Earth. And then here's the satellite way up there, 114,593 kilometers up there. Yeah. What we actually have to do, you're absolutely right, is take that as my radius, but add to that the radius of the Earth. Because we don't want to know how far it is above the surface. We want to know how far it is above the center of the Earth. Right? I think it's 6.38 times 10 to the 6 meters. Is that right, guys? Okay? Absolutely. You got to convert that. So you got a couple of options here. You can tack on 3 zeros to make it meters, or what you could have done, okay, it's completely up to you. You can just write down that number and then put a 10 to the 3 beside it. Okay, it doesn't matter. Okay, let's get the value of that radius here. Let's use our calculator to do that. Let's say 114, it's going to be 114,593,000, or times 10 to the 3, plus 6.38 times 10 to the 6. That gives me a radius of 12097 times 10 to the, what was that? 1, 2, 3, 4, 5, 6, 7, 8. All right. Okay. So we've started somewhere, right? What next? Don't know where to go with this. Don't know how to solve for the period. Everybody knows something for this. Okay. Everybody in this room knows something that I can write down right now. For Jordan, it may be one thing. For Lewis, it may be something else. That's okay. If Jordan knows something and Lewis knows something, then I'm willing to take whatever you got. Okay. Earl, what do you want to tell me there? Okay, so we can use that equation that we derived. I don't want to actually use that directly. I want to derive that again. Every time I see this problem, I want to derive that equation. Now, I'm not going to make you derive it on a test if you get a question like this. Okay, if you write down the equation as I derived it a few minutes ago, that's okay. But I would highly recommend against that because, I mean, look what I did. Lewis pointed out to me that I squared that by accident when I derived it. If you're trying to memorize it, you're even more likely to make a mistake on it, right? So let's derive it each time here. Let's say FC equals FG. Let's say MV squared over R is equal to GM1 M2 over R squared. One of the R's cancels, one of the M's canceled. V squared is equal to G times the mass of the producer over R. Hey, that's perfectly valid. And odds are it's going to help us out, right? But it isn't going to get the period for us. It isn't. Let's get what we can get out of it, though. Let's say V is equal to the square root of 6.67 times 10 to the minus 11. The mass of the producer, which is, the mass of the producer would be the Earth here, right? 5.97 times 10 to the 24. It's on your data sheet. Divided by R, which is that massive number 1.2097 times 10 to the 8. Okay, let's get that speed. I think that satellite's going to have a really fast speed or a slow speed. Slow. Okay. Anybody think fast? Okay, so we got a couple people really fast, a couple people really slow. We'll see here. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. And then let's divide that by the number that we have on the bottom there, 1209, which was our last answer. Now we got to square root that. 1,814 meters per second. That's pretty quick, but it's slower than, honestly, than I expected. Okay. 1,814.29 meters per second. It's quick, but compared to the space station and the space shuttle as it used to orbit around the Earth, it's nowhere close. Nowhere close. Okay, the space station orbits around Earth at about 30,000 kilometers per hour, which is about 8,000 or 9,000 meters per second. 8 or 9 kilometers per second. Way faster than this thing. Okay, got to speed. What now? You know anything else you can do? You don't have to know what you have to do to get the answer. You just look at it and say, okay, what is something else that's valid here? What's something else that I can try? Okay? All right. That is perfectly valid. And odds are, since, look, when we were reviewing, that's what we were talking about. Odds are that's what's going to get us the answer, right? Lewis, we're going to rearrange this to solve for t, right? What's the rearranged form of this equation? T is equal to what? Good. So it's 2 times pi times that big number, 1.2097, times 10 to the 8, divided by the speed, which we found was 1814.29. And when we do the math there, we should end up getting 4.19 times 10 to the 5 seconds. Now that seems like a big number, right? 10 to the 5 seconds. Let's just, out of curiosity, even though they don't ask us for this, let's just out of curiosity figure out how many hours that is. Okay? How'd you figure out how many hours that is? How many seconds in an hour? No, 60 seconds in a minute. 3,600, because it's 60 times 60, right? Okay, so we're going to divide that by 3,600, right? How many hours is that now? That works out to be about 116 hours, which is 5 days. So it goes around the Earth in 5 days. That seems like a pretty slow satellite, right? Well, think about that, guys. Not only are you going around the Earth on the surface or close to the surface, you have a much, much, much bigger circumference to cover if you're 114,000 kilometers above the surface of the Earth. It's a massive distance you have to go around the Earth. So 5 days is actually not that long yet. Yep. No, that's a good question. What happens when a satellite stops working? Well, first of all, a satellite would have solar panels on it so that it could be charged by the sun. So you charge batteries in the sun. Now, eventually, it will stop working, okay? Unless we sent something out there to fix it, which at that altitude would be very difficult. Okay? Satellites that orbit around the Earth at 300, 400, 500 kilometers, we can send spacecraft up there and send out astronauts to fix it, okay, with spare parts or whatever. But that distance, that's difficult. It's not impossible, but it would be difficult. So what happens to them as they start breaking down, as the batteries start or stop taking a charge and the batteries become weaker and whatever? Well, even with no batteries, it should theoretically orbit the Earth without any power. But eventually, it will lose a little bit of its orbit. So it will start losing a little bit of its altitude. But it'll still go around more or less in a circle. But over time, that becomes more and more pronounced, so that eventually what happens is it orbits around. This is what happens, right? It crashes into the Earth. And that's happened before. That's happened before. The good news is, generally these things, before they crash into the Earth, they burn up in the Earth's atmosphere. So we don't generally have to worry about getting hit by a falling satellite. But it has happened before where satellites, military satellites, communication satellites, they've entered Earth's atmosphere. Generally, they're not functioning satellites anymore because whoever puts it up there knows that it's beyond its useful life and it's going to crash. We don't necessarily know exactly where it's going to crash. Okay? They enter Earth's atmosphere, it doesn't completely burn up, and it does crash somewhere. Okay? And I don't know that there's been any known injuries to people as a result of that, because in the end, you look around, most of the Earth is still empty space, right? It could hit somebody, but it's got a lot more chance of hitting that field out there than it does of hitting us, right? But it could. It could. If it doesn't burn up, it could hit somebody. Yep. Well, at the last minute, yeah. Yeah. Like if somebody looked up in the sky, you'd know. No, generally for these things, it's generally they don't know exactly where it's going to come down. They can sometimes say like, we think it's going to be somewhere in the Pacific Ocean, but it's a pretty big area, right? They don't know, they couldn't predict that it's going to come down in Okotoks versus Calgary, let's say. Now, a space shuttle, when they were landing, different, right? Very predictable because they're controlling things. But this is a little bit more difficult. As it enters Earth's atmosphere and we're not controlling it, then it becomes a little bit more difficult to predict that. Here's an example that's not in your book. This is your last example of the unit, by the way. Read this. Okay, just sit at your desk and read this for a second. Don't even copy it out right now. Just read it. And I want you, as you're reading it, to tell me if there's any terms that you don't recognize there. Any terms that seem kind of weird to you, that you don't completely understand. Anything? Anything in here that you've never heard of before? There's got to be one word in there that you've never heard before. Geosynchronous, she says. The geocentric theory of the solar system or of the universe said that the Earth is the center of the center of the universe, right? Geo means Earth. Geocentric means Earth-centric. Geosynchronous means in sync. So geosynchronous would mean in sync with the Earth. So what that means is, guys, you look up in the sky, you see a satellite, if you could see the satellite. 4 hours later, you look up in the sky in the same spot, you would see the satellite in the same spot. So as the Earth rotates on its axis, the satellite goes along with it. Here's the Earth. Here's Calgary. Here's a satellite. 6 hours later, here's the Earth, but Calgary is right here. Where's the satellite? Right above Calgary. This satellite orbits around the Earth, but maintains the same position above the Earth all the time. Why? What would be the benefit of that? Why would we want to do that? Yep. Could be. That's right. If you're in Calgary here and you see this satellite, and then 6 hours later you see it there, okay, let's say you're in Asia, you can't see it, right? You're in the shadow of the Earth there, right? You're never going to see it, right? So you'd have to have, for whatever the purpose, a geosynchronous satellite above you or somewhere nearby you. Why would you want to have a geosynchronous satellite? Well, generally geosynchronous satellites are for communication. Okay. How many people have satellite TV? You got a little satellite dish receiver on the side of your house or on the roof of your house, right? Where's it pointing? Where's it aiming? Well, towards a satellite in the sky, right? Well, if that satellite doesn't maintain the same position above the Earth, let's say it makes 2 orbits around the Earth per day. Well, then that means you're going to get a good TV signal twice in a day as it passes above the satellite receiver. We don't want it to be orbiting in a different position above the Earth all the time. You're going to have to keep moving your receiver in order to see it, in order to detect the signal from it. You need it to be in the same spot. So when the guy comes to install your satellite receiver, he aims it at the satellite, and it's always aimed at the satellite because the satellite's always there in the same position. That makes sense? Now, obviously, you're not going to have just one television satellite above the surface of the Earth. There's going to be dozens or even hundreds of them because you have to be able to reach them from basically any part of the Earth. Yep. Yeah, I don't know that it would be a geosynchronous satellite, though, to determine, say, a hurricane, take pictures of a hurricane or something like that. Certainly, yeah, certainly you take pictures of weather, hurricanes, whatever, by satellites. I'm not sure that would have to be geosynchronous, though. Like a military spy satellite, for instance, they can move around. They move it to take a picture of, one day they want a picture of, some camp in North Korea, and the next day they want a picture of, something in Afghanistan. They can move that satellite around. That wouldn't be a geosynchronous satellite. And I suspect the satellites you're talking about would be the same. They can move them to wherever they wanted, I think. All right. We want to find the height above the surface of the Earth that a satellite would have to be placed in order to make its orbit geosynchronous. The issue that I have with this question, I think, is that I don't have any numbers. Like, how can I solve for a height if I have no numbers? Yeah. Okay. So, guys, this is perfect. Okay. Lewis just raised his hand, and he's basically telling me something he knows. I don't know if Lewis knows how to solve this problem yet. I don't really care right now, to be honest, if he knows how to solve this problem. He's told me something that he knows, something that he can write down. Okay, so let's do it. Lewis says, I know what G is. It's 6.67 times 10 to the minus 11. And I know what the mass of the Earth is. It is, what is it? 5.97 times 10 to the 24 kilograms, right? Okay, good, good. So Lewis has given me a couple givens here. Anybody else? Maybe another given, maybe an equation, maybe it's just some kind of concept. Okay, Carrie? Be careful with that. Little g is 9.81 on the surface of the Earth, but we're not on the surface here, right? So we're not going to write that one down. Okay, that's not a valid thing because that's only valid for the surface. Okay, we're not there. Jacob, is your hand up or no? Okay, the radius of the Earth, 6.38 times 10 to the 6. Okay, there's something else. So all of a sudden we're getting some numbers here. Yeah. How? Okay. So Aiden's saying we want to find the period of orbit around, okay. We want to find the period of the Earth's rotation. That would be the same as the period of the space of the satellite, right? Because it maintains the same position. So if the Earth rotates in 6 hours, then the satellite's got to orbit around the Earth in 6 hours, right? Oh, you are so on the right track here, Zane. Okay, okay. Yeah, you can. So basically it comes down to FC is equal to FG, right, Zane? V is equal to, okay, okay, fair enough. Let's get rid of this. You know what, let's not, because somebody's going to give me that one in a second here. So let's leave that one up there. And then let's say V is equal to 2 pi R over T. All right, good, 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 good. We kind of went away from what Aiden was saying there, and I kind of want to go back to that. Aiden said, what did you say, Aiden? We want to find the period of the Earth's rotation, but you're not sure exactly how to do that. Anybody? Right, was your hand up before? Just for one of these, though? What is it? Oh, okay. So Brian's saying the period of the Earth's orbit and the period of the satellite's orbit around the Earth is the same. Yes, that makes sense, right? Makes perfect sense if the satellite is maintained in the same position, right? The Earth takes 6 hours to rotate, then the satellite's going to take 6 hours to go around the Earth. Okay? The period is 24 hours. How long does it take the Earth to rotate on its axis? 24 hours. It's a day, right? So now we have, that's a big deal right there, because now we have the period of this satellite's orbit around the Earth. We know it's 24 hours. Okay, I think we're ready to start plugging numbers in here. You got something else for me, Lewis? Okay. Okay, 86,400 seconds. Yeah, we know we're going to have to do that. That's a fairly minor thing. It's really important when we go to use that number that we have seconds, but conceptually it's fairly minor because we all know how to do that, right? Multiply by 60, multiply by 60 again. Okay, let's start plugging some numbers in and see what we can do here. I don't care which one you start with, this one or this one. Okay. Zane suggested that I use this equation. That's the first equation that we came up with. So let's try that one first. Doesn't get me anything, then I'll try the other one, right? So let's say V is equal to 2 pi r over t. 2 times pi times r. Ooh. Okay, the radius of the Earth is 6.38, but I don't know what the radius of the satellite's orbit is, do I? I know it's 6.38 plus how high it is above the Earth, right? Yeah? Oh, careful. No, it's not. No, it's not. Okay, Lewis just said it's geosynchronous. If we find the speed of the Earth orbiting, it's the same as the speed of the satellite. No, the satellite's a lot further out, so it's got a much bigger circumference that it has to cover, right? And it does it in the same amount of time. So if it has to cover more distance in the same time, that satellite's going to have to go faster, right? Make sense? We don't know what V is. We don't know what the speed of the satellite is. We don't know what the radius of the satellite is. We know it's related to this, but we don't know exactly what the value is. T we do know, though. It's 86,400 seconds. So Zane gave me an equation, 2 pi r over t. We got a number for that, but we got two unknowns. So right now it wasn't very helpful, but it's not wrong. It's perfectly valid. So we're no further behind where we were. Let's go back to this equation, the other one. The mv squared over r equals gm1 m2 over r squared. See if that gets me something. If it doesn't, I don't know what to do. But we still haven't exhausted this option yet. V squared is equal to g times m over r. Has to be the mass of the producer, right? V, we don't know. G, 6.67 times 10 to the minus 11. The mass of the producer is 5.97 times 10 to the 24 divided by r. Uh-oh. 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 We got two unknowns in this one, too. What do you notice about these two unknowns in these two equations? Oh, come on, you math people, you math whizzes, you. What do you notice about them? Yeah, you got to be careful with that. But yeah, in the end, you can do a little substitution thing because it's the same two unknowns. It's the same two unknowns. We don't know V and R in the first equation. We don't know V and R in the second equation. Here's what I want to do. Okay, here's what I want to do. Let's call this one equation number 1. And let's call this one equation number 2. Let's take one of those two equations and solve for something that we can make equal to the other one. Let's take equation number 2 and square it. This might seem odd, but If we square equation number 2, this is what we end up with. V squared is equal to 4 pi squared times r squared over, see what I'm doing there, guys? I can square that equation number 2 as long as I square everything in that equation. Okay, the bottom would be 86,400 squared. So that's my new equation number 2. It's the same thing, but I've just, well, usually we try to simplify things. I haven't simplified that at all. I made it kind of uglier. But the reason I've done that, here, I'll get your question in 1 second. That's my new equation number 2. The reason I've done that is because now both of those equations have v squared. If v squared equals v squared, 4 pi squared times r squared over 86,400 squared equals equation, this is equation number 2, equals equation number 1. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by r. You got that? Does it make sense? That's ugly math, isn't it? Would you have ever thought to do that on a test? Probably not. Okay, we're going through this question because it's good mental exercise, but you're not going to get something that's this hard on a test. But I'll tell you what, there is no reason why whatever we see in blue there, we can't come up with. Okay, you guys are perfectly capable of writing down everything that's in blue. Once we get to the green and the red, that's when it becomes a little bit unfair for a test question for you guys. All right. Let's solve for r. We've got to combine them. It becomes 4 pi squared r cubed, because this r goes up by multiplying, right? Over 86,400 squared equals 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Oh, this is almost as bad as that inclined plane slash pulley slash elevator slash projectile motion question that I gave you guys back in Unit 2. Almost as bad as that, isn't it? Worse, say? I don't think it's worse. Let's do this on a calculator here now. Okay. Let's get the number on the right-hand side, because that's the easy one here first. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Okay, that's the number on the right-hand side. Let's take the 86,400 up by squaring it, times 86, or by multiplying, I should say, times 86,400 squared. Okay, so now I'm getting rid of the 86,000 on the bottom. Let's divide that by 4 pi squared. We'll use some brackets here. 4 times pi squared. R cubed is equal to 7.5295 times 10 to the, what was the number there? 10 to the 22? Now I've got to take the cube root of that. How do I do that? How do I take the cube root of that? So it's not the square root, it's the cube root. Where is it? Where's the math function? Math, and then at number 4. You could actually use number 5 as well. That allows you to take the cube root of the whatever root of it. Okay, so that's a function that you don't often use, so it's within your math functions there. The cube root of the answer that I just got. You get 4.2227 times 10 to the, oops, times 10 to the, what is it? 1, 2, 3, 10 to the 7. Phew. After all of that, some pretty ugly math there. We end up with something that's not the right answer. Oh, but we're close. We're close. There's a little bit more math involved, but the math involved now is easy. What do I still have to do here? Earl? Yeah. We want to know the distance above the Earth's surface, right? We just found the radius to the center of the Earth here. So let's take that number, 4.2227 times 10 to the 7, and then subtract the radius of the Earth, 6.38 times 10 to the 6. And when we do that, we end up getting 3.58 times 10 to the 7. Above the Earth's surface. Wow, is that an ugly question or what? Yeah, but I'm telling you guys, I still contend that conceptually, you guys are fully capable of understanding this question. Fully capable of doing this question conceptually. Now, the math involved, maybe not. Maybe not. Okay, but physics-wise, you can do it. You won't get a question that's this hard on Monday's test, I promise you that. Yep, Carrie? Yep. The two blue ones, you mean? Yep. Couldn't I just square root this? Yeah, I could have. Yeah. Yeah. So what I did is squared this equation number 2 to make it v squared so that I could set v squared equal to v squared. Carrie said, couldn't we have square rooted equation number 1 and then set v equal to v? Absolutely. We would have ended up with this. We would have ended up with the same ugly math there, Carrie. It would have looked a tiny bit different, but it wouldn't have been any easier. Wouldn't have been any harder. Just would have been essentially the same ugly math there, but it would have worked. Yeah. Any issues there? All right. How many people kind of followed? Yeah, forget about the green and the red here. Forget about the green and the red. How many people followed me or with me with the blue here? Good. Good. That's where I want you to be. Okay? That's what I want you to get here is what's in blue. We just finished it off with the green and the red here to show you that, look, we can actually solve this. It's just tricky mathematically. Yeah, Lewis? The answer was 3.58 times 10 to the 7 meters. So geosynchronous satellites, what we're saying is they're really high up. Okay, they're really high up. The space station is 10 to the 3 meters up. Okay, this is about 10,000 times higher up than the space station is. So good news is you don't have to worry about colliding with these puppies because they're not 10,000 kilometers up. They're 10,000 times higher than the space station is. Got it?